Hey guys, quick biochemistry basics here. Let's talk about differential interference contrast or DIC microscope. DIC microscope is a microscopy technique that gives you 3D images of the specimen. These 3D images are not real 3D image, but while looking at the image, it seems that the sample is illuminated from one side while the opposite side remains dark. Now remember, there is no light coming from the sideways. The sample is always illuminated from its bottom. But when the image of the sample is formed, it seems that it has been illuminated from the sideways. The optical phenomenon used in DIC microscope involves lots of physics. So please pay attention and watch this video till end. I will be covering all the physics involved in DIC microscope. So let's get started. First, let's talk about polarizers. The light is made up of electromagnetic radiation, and the electromagnetic radiation is made up of electric and magnetic field vectors. To make things easy, here we will consider only the electric field vectors. The unpolarized light have electric field vectors oscillating in all directions. When this light passes through the polarizer, only the electric field vector oriented in particular direction passes through the polarizer, whereas rest of the electric field vectors are blocked. We can now have the second polarizer, also known as analyzer, placed next to the first polarizer. If both of them are parallel to each other, then the electric field vectors will pass through the analyzer and absorbed easily. If the analyzer is crossed at an angle, then the intensity of specimen observed goes down. When the analyzer is at 90 degrees with respect to first polarizer, then the electric field vectors is completely cancelled out and no intensity of the specimen is detected. Nomarski prism. Nomarski prism splits the coming ray of light into two parts. One of them is known as the E-ray or the extraordinary ray, and the other is known as the O-ray or the ordinary ray. The difference between E-ray and O-ray is that the electric field vectors are oriented 90 degrees with respect to one another. What I mean is, if the E-ray has electric field vectors oscillating vertically, then O-ray will have electric field vectors oscillating horizontally. Now let's see the schematic diagram of DIC microscope. At the bottom, we have the condenser, which is just like the condenser of bright field microscope. Next, we have the polarizer, and it is placed at an angle of 45 degrees. On the top of polarizer, we have the Nomarski prism. Next, we have the objective lens, just like the objective of bright field microscope. On the top, we have the second Nomarski prism, followed by the polarizer, which is at an angle of 135 degrees. Finally, on the top, we have the eyepiece to see the specimen. The angle of polarizer and analyzer can be changed as per user wish. Here we are using 45 degrees and 135 degrees just to make things simple. Now let's see the working of DIC microscope. The light from the condenser enters the polarizer and gets splitted into E-ray and O-ray by Nomarski prism. The distance between E-ray and O-ray is also known as the shear distance. The E-ray and O-ray further travels through the specimen and encounters the second Nomarski prism. The second Nomarski prism again combines E-ray and O-ray into a single ray, which then passes through the analyzer and finally the eyepiece. The image that you obtain looks like a 3D image, where one side of the image is bright while the other is dark. But in reality, there is no light coming from the side of the specimen. The light is hitting the specimen only from the bottom. So the question is, how do we get an image where one side of the image is bright while the other side is dark? So let's try to understand the physics behind DIC. First, let's understand the wavefront. Wavefront is a plane perpendicular to the ray of light. So in this case, we will have two wavefront, one for the E wave and other for the O wave. An interesting thing about E wave and O wave is that both have different velocity while traveling through the Nomarsky prism. As a result of different velocity, there is a phase difference between E ray and the O ray. Just like we saw in the ray diagram, both these wavefronts are separated by shear distance. Now things get interesting when both these wavefronts hits the specimen. As the specimen is dense and have greater refractive index as compared to air, the velocity of light traveling through specimen decreases. As the wavefront travel further, they encounter second Nomarsky prism. It is over here, both these wavefronts are now combined. When E wave and O wave meet, something interesting happens. The point where there is no phase difference between E wave and O wave, the resulting electric field vector so formed is at 45 degrees. Now the second polarizer or the analyzer is crossed at 135 degrees. So when this electric field vector, which is at 45 degrees, passes through the analyzer, it is completely blocked, and as a result, this region of the specimen is seen as dark. If we see the wavefront of the other region of the specimen, then there is a phase difference between E ray and the O ray. As both these waves are not aligned, there will be many resultant electric field vectors, and the final result of such many electric field vectors is the formation of elliptically polarized light. And the elliptically polarized light can easily pass the analyzer as there are many electric field vectors. Only the one with 45-degree angle will be completely blocked. The rest of the electric field vectors will still pass the analyzer, and as a result, this region of the specimen is seen as bright. So here we go. One end of the specimen is seen bright and the other end is seen as dark. It appears that the image of the specimen is three-dimensional, but in reality that's not the case, as lots of physics is involved. Besides the specimen, the wavefronts coming from the background also shows the phase difference. Hence, the background observed will be also bright. Now, before we end this video, there should not be any confusion with the phase contrast microscope. The phase difference involved in DIC is completely different as compared to the phase difference of phase contrast microscope. Remember, in DIC, the phase difference is between the E wave and the O wave. It's between the electric field vectors of E wave and the O wave. This phase difference finally results in an elliptically polarized light, which then passes through the analyzer and seen as a bright image. In case of phase contrast microscope, the light used first of all is not polarized. When this light passes through the specimen, there is a decrease in the velocity of the light. If the ray of light coming out of specimen hits the phase shifting ring, then there is a further decrease in its velocity. Finally, when these waves are combined by the eyepiece, two things will happen. The ray coming from the phase ring will undergo destructive interference because of its decreased velocity and phase shift. Here, this region of the specimen is seen as dark. The ray of light that fails to hit the phase ring will not undergo destructive interference, and this region of the specimen is seen bright. Hence, remember, in phase contrast microscope, the phase difference between the light rays results in destructive interference, which gives rise to dark areas of the image. In DIC, the phase difference between two polarized waves, E wave and the O wave, give rise to an elliptically polarized light, which passes through the analyzer and it's observed as a bright region. So phase contrast microscopy and DIC microscopy are completely different, hence do not mix them up. I hope DIC and phase contrast microscope should be clear by now.